All right. I am delighted to introduce Duncan Watts to the Complex Systems seminar today. He's had a sort of career through a handful of fields, all of which sort of, really form a lot of the core of complex systems, from a PhD in theoretical and applied mechanics, now then into a department of sociology, a stint in industry at Yahoo Research and Microsoft. And he's now joining us from the University of Pennsylvania, where he's in computer and information sciences, communication, and operations information decisions, all at University of Pennsylvania. So Duncan, so I'll keep an eye on clarifying questions, and then otherwise we'll save questions for the end. Thank you.
Hello? Okay, great. Thanks. I think you had to unmute me there, Abby. Thanks, Abby. It's great to be here. Michigan is one of my favorite places, so I'm really happy to talk to you all. I want to share some recent work that's joint with Abdullah Al-Matouk, who was an intern of mine a few years ago at Microsoft Research and is now an assistant professor at MIT School. Mohammed Al-Sabeh, who is Abdullah's PhD student there, and Ming Yin, who was a former postdoc at Microsoft Research, who is now an assistant professor at Purdue University in computer science. So it's a complex systems talk, so I want to talk about complexity, but I want to talk about a particular type of complexity, namely with respect to tasks. And the broader motivation for this study and some other, a larger project that I'll mention briefly at the end, is that we're interested in how groups of people solve problems. And as you probably know, this is a big topic that goes back several decades, 60 or 70 years at least, in several different fields, in psychology and management science, sociology, economics. So it's a question of great academic interest. It's also a question of great practical interest. As Abby mentioned, I spent some time in industry, actually 12 years at Yahoo and Microsoft. And there's a lot of attention paid to teams in those contexts, because most work gets done in teams. And so everybody is very concerned about, how in practice you can make teams work better. What is endlessly surprising to me about questions like this is that, given all of the time and attention and importance of these sorts of questions, all the time and attention that has been paid to them and their importance, it's always surprising to me how even the most basic questions are in some sense unanswered. And the question that I want to focus on today is, in a way, the most basic question of all, which is, when should we even bother to use groups? And that might seem like a puzzling question to ask. So let me try to clarify it a little bit with reference to this very nice survey book by James Larson called In Search of Synergy in Small Group Performance. And the question that he is asking in this book is effectively, when should you use a group to solve a problem versus some collection of independent individuals? And the way to analyze this question a little bit more is to compare what he calls an interacting group, which is what you're thinking of as a group, people who are working together, talking to each other, interacting in some way, collaborating to solve a problem, with what is called a nominal group, which just means an equal sized collection of individuals who are not interacting, who are all trying to solve the problem independently. And the reason for comparing interacting groups with nominal groups rather than just with single individuals is, of course, that you want to try to make an apples to apples comparison. So if you have 3 or 5 or 20 people in a group, it doesn't really make sense to compare their performance with that of a single person, but it does make more sense to compare it with a similar sized group. So that's can you hear me? Sorry, my Zoom is telling me that I'm having problems here. So the word synergy refers to precisely the overperformance of groups relative to a nominal group. So it's sort of you're trying to net out as much as possible about group size and just focus on the interacting part. And it's to the extent that interacting groups outperform nominal groups, you could say they display synergy. Even here, you have to be a little bit careful. There are different types of comparisons you could make, which correspond to different types of synergy or different levels of synergy. And I'll just use Larson's terminology of weak versus strong synergy. For weak synergy, you just mean that your group is outperforming an average member of a nominal group. And for strong synergy, the group is outperforming even the very best member of a nominal group. So that's probably what you want when you think about it naively. But it turns out that in the literature, strong synergy is pretty rare. People have been doing lab experiments for a long time. And when they do this comparison of interacting groups with nominal groups, very often they find that some sort of weak synergy is realized, but pretty rarely do they find that strong synergy is realized. So, I think that's probably the, the 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 holy grail of this area is to try to find conditions under which we should reliably get strong synergy. So how might we do that? And there are lots of ways. I'm only going to talk about one of them today. There's a whole, I'll actually come back to this part at the very end. You might think that how you put teams together, the particular people that you put together in those teams could have an impact on synergy. So these are group compositional factors. So just think of anything that you could measure about an individual and now treat them as some sort of vector of features, and you want to try to combine those vectors in a way that produces the best group performance. You could also imagine that there are other factors that are not specifically related to the individuals or immediately related to the individuals, but are still related to how the groups interact with each other, like the kind of leader that they have or the kind of leadership structure that they have, possibly networks of communication, other kinds of modes of communication. So all of these group process factors might also plausibly affect synergy. And then finally, there are task-related factors. You could imagine that different types of tasks might lend themselves towards synergy more than others. And I'll come back to that question at the very end. But the one I want to talk about today is that the complexity of a task might also be relevant. And by the way, Abby, I see that there are chat questions coming up, but I don't have enough sort of screen space to track them. So if you see something come up in the chat that you think I need to address, please let me know.
I'm keeping an eye on, and there was going to be a clarifying question about different types of tasks. So you're already got there.
Okay, we'll come back to that.
Yeah.
Right, so what I mean by task complexity, at a high level, it's relatively easy to define that we mean something like the number of components in a task, the strength and number of interdependencies between those components, and the roughly the time scale on which things change. This, I think, will sound pretty familiar to all of you. It's very similar to what we mean by complexity more broadly in complex systems. And it's pretty intuitive that if you take a task with more components and more interdependencies, and you require that it be executed on shorter timescales before everything changes again, that task seems clearly harder or more complex in some way than a task with fewer components or fewer interdependencies, or for which you have lots and lots of time to sort everything out. It's also plausible that complexity could have some impact on group synergy, i.e. the difference between interacting and nominal groups. But here the direction is less clear, right? So groups are doing lots of things. They're doing some good things and they're doing some bad things. Groups can distribute effort. They can check each other's errors, they can avoid redundancy, and some past work of mine with colleagues at Microsoft has shown that for larger groups, those benefits can outweigh the costs. But there are real costs, and those have been documented extensively in the literature on groups. They're referred to basically as process losses. So, social loafing or free riding is one very common process loss, that people tend to not work as hard when there are other people around also doing the work. Groupthink is another common type of process loss, where everybody zeroes in on or zooms in or coalesces around a particular type of solution rather than exploring the space of possibilities. Conflict, competition, there's all kinds of negative dynamics that happen inside of groups that can cause them to underperform an equivalent number of individuals. So it's just not clear that as the complexity of the task increases, whether the positive effects of group membership should outweigh the negative ones. So it seems that this could happen. It's not clear that it does happen, and if it does happen, it's not clear what direction it's in. So that's really what we're going to be focusing on here. But the problem, the analytical problem that we have in studying complexity, is that complexity, it turns out, is itself complex. And going beyond that very qualitative, high-level definition that I gave earlier to something that you could really, apply to a real-world task, something that's more than just a toy problem, is, it turns out, extremely difficult. And so a paper about 10 years ago by Liu and Lee tried to bring some clarity. And they summarized a bunch of different definitions in the literature. So they found 24 distinct definitions of complexity. And then they tried to sort of pull it all together with their own model, which you can see on the right here, involves 27 complexity contributing factors grouped under 5 task components and 10 complexity dimensions. So, that, I'm not sure that that really brings clarity to the problem. It shows in some ways how difficult the problem is to clarify. In addition to the sheer complexity of the model, many of these factors are themselves kind of difficult to operationalize in terms of in a task independent way. So the result, and it's I may have missed something, but my assessment of this literature is that it is difficult, if not impossible, to take some measure of complexity, some well-defined formalized notion of complexity, and use it to generate numerical values that you can compare with each other in an apples to apples way across different types of tasks. And so it's very difficult to say in a very well-defined sense that this task is more complex than this other task by this amount. And as a result, varying complexity and studying how things change in response to varying complexity is pretty hard to do.
And so, sorry, just a quick question following up on that, which I think is related to this point. A question is that why is time available to complete a task an element of the complexity when that might just be something that affects the probability of success?
In the following sense, that if you like cast your mind back 100 years now to the Ford Motor Company, where they bring out a new model car every 10 years. This was the company that really pioneered the notion of vertically integrated production. And the initial design phase of building that first Model T Ford probably involved resolving a bunch of interdependencies and complexities. But then the design doesn't change for a decade, and so you just, everybody finds their, highly specialized role in producing these cars, and you can just sort of crank them out, and a a very simple, chain of command, hierarchical form of organization was developed that worked pretty well for solving that kind of problem. So, in some sense, the task was complex, but the complexity all disappeared because you had, in some sense, infinite time to solve the problem. But fast forward to 50 years later, and since then, now you have to constantly produce new models which introduce new interdependencies, which require you to resolve the problem of solving the problem all over again. And so now the complexity is dramatically, at least if it's not increased, it's made more salient, right? So the problem is now complex in a way that it wasn't before, because you're constantly solving the design problem at the same time as solving the production problem. And so, anything in technology has this, and again, like working in technology companies, you see this all the time, that, you're always redesigning the system that you're building because somebody else has come along with some innovation that will otherwise outcompete your product. So I agree with you that time seems different than the other things that I mentioned, but if you leave time out of it, in some sense, if you have infinite time, like nothing is complex, right? I mean, put it another way, like I have friends who have like built cars by themselves, right? It is possible to do that. You can pull apart a car and you can rebuild it entirely by yourself. It just takes you like a year to do it. And so, like, that's clearly not how we want to build cars. So you can sort of, in some sense, resolve the complexity by having infinite time to do things. So you kind of have to keep time in there as a constraint. Anyway, that's my best justification. I agree with you that it looks different, but I think you need it in there. Does that answer the question? Of course, I can't even hear you.
Yeah.
Okay, great, thanks. Anyway, we're gonna, having introduced all this problem with defining complexity, our solution is to try to sort of avoid it completely. We're not going to solve this problem of creating a formal language for task complexity. I would love to solve that problem, but we have not solved that problem. Instead, what we have done is identify a class of tasks where we can vary complexity in a systematic way. So we can establish that certain instances of this task are more complex than others without changing anything else about the task. Okay. And I'll tell you what the task is in a moment, but we also have some nice to have properties as well, because we want to do experiments. Because we want to compare interacting with nominal groups, the task necessarily has to be something that people can do on their own independently in some reasonable amount of time, as well as in a team setting. It has to be something where we can recruit a bunch of people from, a crowdsourcing website like Mechanical Turk, and give them some minimal training and have them do it again in a reasonable amount of time. And then ideally, we'd like something that maps to real world tasks. So, we don't want to, for example, study NK problems because at least I am unable to map them to real world tasks. So, so we want something that's a little more intuitively, has a little more external validity than that. So the sort of compromising between all of those criteria, the tasks that we're going to study here are called constraint satisfaction and optimization problems, which is really just a resource allocation problem where you have some objective function that you're trying to maximize, and then you have a set of constraints that you have to obey. So these problems are widely studied in AI, a lot in operations research. And so they do, in fact, map to real world problems, including very recently problems to do with COVID. So allocating vaccines and medical supplies, et cetera. So there it's very clear that you have some valuable resource. You're trying to optimize for some outcome, which might be, uh, or some complicated outcome, which could be a combination of reducing future cases or hospitalizations or deaths, maybe some other fairness considerations. Well, actually, you could consider the fairness considerations to be constraints, right? That you have certain other priorities that you would like to satisfy in addition to, optimizing your outcome. So there are lots of examples of real world versions of this problem. We're going to study a pretty toy version of it, but hopefully it will make sense. And then you can tune the complexity of these problems by tuning the parameters, and you can imagine this in the sort of standard rugged landscape idea of complex systems where you have a bunch of globally suboptimal solutions that are locally optimal, and so it's easy to get stuck. Okay. So here's the exact task that we're going to study. It's called a room assignment problem. So you have the setting is that you have a bunch of students and you have to assign them to dorm rooms. The students have different preferences for different rooms. We could talk about faculty and offices as well if you like. Um, and they also have constraints. So some students don't want to be neighbors with each other, and some of them definitely want to be neighbors with each other. So we can invent as many of these constraints as we want. And the three parameters that control the complexity of this task are the number of students, the number of rooms, and the number of constraints. So uh, just to show you a couple of examples, and having talked all about time, we're going to basically set that aside and fix the amount of time that uh, 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 the groups have to solve this problem. So everybody gets 10 minutes to solve these problems. And for an easy problem, that seems fine, right? So this is a problem that involves 6 students and 4 rooms and 2 constraints. So you probably look at that and think, no problem, I can solve that problem. Probably find the exact optimal solution in 10 minutes. You can make it harder by adding more students and more rooms and more constraints, and then you can make it harder still. And now it's starting to look pretty hard. And in fact, this is a pretty hard problem to solve. So, just sort of visually, you can appreciate that by tweaking these parameters, you can make the task more complex in the sense that we have described. And again, you could also make it more difficult by increasing the time constraints, but we're not going to do that here. Okay, so this is sort of the general picture. We can vary complexity from top to bottom. We give people some initial state that they have to solve. They then move students around until they get a valid solution, having or what we call a complete assignment. Having found a complete assignment, they can then continue to meddle with it because they might not have found the optimal one, and then eventually they're satisfied with their solution, or they just want to move on, or they run out of time, and they submit it. Okay. Now, an added wrinkle here is that we want to be able to assign people to teams in a particular way. And so we're going to first measure individual level features about them, and then run a second phase of the experiment where we assign them to teams. So in the first phase, we recruited 1,200 participants, and we explained the problem to them, gave them some training, and then all of them completed 5 of these tasks by themselves. So no teamwork in phase 1, just individuals. And also we gave them pretty easy tasks to solve because we wanted them to have a good experience and come back and participate in phase 2. We used the moderate difficulty complexity tasks to rate their skill. We also gave them a reading the mind in the eyes test to measure their social perceptiveness. If you're not familiar, this is just a very standard test. You can see the picture at the bottom here. You get a series of photos like this one where you just see people's eyes, and you have to say what emotion is being expressed. And it's something like 30 odd of these pictures, and you get a score. And it turns out that is a relevant way of characterizing how socially perceptive people are. In phase 2, which happened a few days later, we re-recruited about 800 of the same participants, and this time, based on the measurements that we had made for them in the previous, in phase 1, we assigned them to blocks. So we used randomly assigned them in blocks to one of 6 blocks. So we had high skill, high social perceptiveness, mixed skill, high social perceptiveness, etc. You can see the 6 blocks over here on the top right. And then within each block, they were assigned to either a team condition or to an individual condition. So about roughly 2/3 of them were assigned to groups of 3, and the other third were assigned to an individual condition. Now, in the group condition, it looks very much like the screenshot that I showed you earlier, except over on the right-hand side, you can see that you get a little avatar for yourself, and you see some avatars for your 2 team players. And there's a chat window that allows everybody to talk to each other. And then the other difference is that if one of you is in the process of moving a student to a room, which you do by dragging it with your mouse, then that person becomes locked for the other 2 players. So we resolve conflicts that way. So 2 people can't be sort of trying to move the same person at the same time. And then the other way in which people interact is that the solution can be submitted only with consensus. So everybody has to agree to submit the solution. In this phase 2, we introduced a wider variety of complexity. So we had one very, very easy task, low complexity, medium, high, and very high complexity. So we gave them a much more stringent test in the second phase. Okay, so are there any, let's see.
A quick question about the sampling from Amazon Mechanical Turk, how you're choosing the sample or how representative they are?
Well, they're not representative. That's a convenience sample. We did look at I don't remember the demographic breakdown. They're definitely more diverse than a typical sample of undergraduate students at the University of Michigan, but they're not in any sense a representative sample of the U.S. population, nor are they in any experiment really. I mean, I think that's pretty normal. So yes, I think Turk is not perfect, but it's actually surprisingly good in terms of finding people who take the task very seriously and really devote effort to solving these problems. I'm always surprised at how diligent and serious the Turkers are for these experiments that we've run for many years now.
And maybe at the end you could talk a little bit about just virtual lab experiments more broadly, knowing this is something that you do more of. But another just one question more about, I guess, would it make a difference if they were communicating verbally or spontaneously? If you think sort of English fluency and typing proficiency is important in this setup? and if it's correlated with it.
It could be. We select on people who have very high ratings for previous work. So everybody is already done a lot of work on Turk, and it's almost all English language. So I think that certainly could be a factor. We didn't try to evaluate that, but absolutely, you could imagine that things are different in person versus online, typing versus talking. I think all of these, and we'll come back to this question at the end because, and again, you could ask these questions of like any experiment that's ever been done. There's like always a bunch of nuisance factors that get what people call nuisance factors that get sort of fixed in the experimental design, and you could imagine that changing any of them could have some effect on the results, and that's always a relevant thing to think about.
Excellent, thanks.
Okay, so we have 3 different performance measures. We measure their normalized score, which is just the score that they got divided by the maximum score that they could have got. We do that because different levels of complexity. So the bigger the task, the more students, the bigger the higher the maximum score you can get. So we just normalize things out. The duration is just how many minutes or seconds it takes to submit your solution. Again, it times out at 10 minutes. It turns out that is not really a binding constraint for almost anybody. And then efficiency is just the score divided by the duration. So you can see here that this is really just a manipulation check. We want to make sure that the thing we're varying is having the effect that we think it's supposed to have, and it does. So as you go from very low complexity to very high complexity, the scores go down. They actually go down by a lot. It turns out that the typical scores for all of these experiments almost all range between 80 and 100. So there's only about 20 points variation at all between best and worst performance, and we're seeing about half of that range being realized in terms of average performance. So we're going down from 95 average to 85 average. So that's actually a pretty big difference. The difference in duration is even more obvious. That we're going from about 2 minutes to solve the problem to about 6 minutes. So they're doing worse in terms of score, and they're taking about 3 times as long to get it. So these are big effects of complexity, which is exactly what we hope to see. And then efficiency, of course, is plummeting as complexity increases. Okay. So what we want to ask is, how does synergy depend on this? So again, weak synergy is just the group doing better than a randomly selected member of a nominal group, and strong synergy is the group outperforming the best member of the nominal group. Because we have 3 different performance measures, we have 3 different notions of best. The individual who scores the highest, the individual who is the fastest, and the individual who's most efficient. So we have 4 different comparisons, right? Random, highest scoring, fastest, and most efficient. So we're going to measure all of those. Somebody's asking about the algorithmic complexity of the actual task. Yeah, it's a good question. We really had hoped to leverage that more. It turns out that there's not an analytical formula for analytical complexity for this particular task. You can use standard solvers and just measure the runtime, but that actually varies a lot from realization to realization, and it correlates pretty closely with the solution, the scores that humans realize. So in the end, we just are, you know, effectively replacing what we would call subjective complexity for objective complexity. So I think it would be nice to have a, you know, a formula that was not at all dependent on the people solving the task, but that actually turns out to be pretty messy. So we're really just demonstrating here that we're varying these parameters and they're having the effect that we hope they'll have, which is that the subjective complexity for both individuals and groups is responding the way that we hope it will. Okay, so it's not ideal, but that's the best that we could do. Okay. Right. So what are the results? So there's a lot in this figure here. Let me just focus on the top panel here. So this is showing standardized scores, and you can see, so they're standardized, right? So we're within each complexity category, we are looking at the relative performance of the different groups relative to each other. Okay, so I apologize that that green dashed line is actually kind of distracting because you can't really compare performance across complexity categories. Everything's getting worse, as I just showed. Everyone's doing worse with respect to score. So these you really should be looking within category, and you can see that for all of the complexity levels, the green bar, which is the interacting groups, is outperforming everything except the orange bar, which is the best individual comparison. So this would be an example of weak synergy that is consistent or unconditional, right? That we're seeing consistently that interacting groups outperform random individuals, and they outperform fastest and most efficient individuals, but they don't outperform the very best individuals for any level of complexity. For duration, we see something quite different. So for lower complexity levels, the interacting groups are actually the slowest of all the comparisons that we're making. But as complexity increases, they become the fastest, right? So they're going from worst to best. And then when you combine those two, the efficiency, in terms of efficiency, you see this very clean transition that is really dominated by speed, right? That they're doing roughly as well as even the best individuals, but they're doing it quite a bit faster. Okay, and so for duration and efficiency, you see strong synergy, but it's conditional on complexity, right? So you go from something where there's no synergy at all. In fact, you're doing worse than to individuals. But as the tasks become more and more complex, it becomes better to give it to the group. Okay. I'm sorry, I'm just trying to read these questions here. I'll get to the composition question at the end, Jaron. You didn't miss it. I haven't talked about it. Yeah, so we're actually not looking at group composition here. We're just lumping all the groups together and comparing them to individuals. But we're comparing them within blocks. Okay, so everything is an apples to apples comparison here. In the duration case is best to find. Yeah, so okay. So best here means highest scoring. This is maybe that's not a very good term there. Best means highest scoring. Fastest means fastest, and most efficient means the highest ratio of score to speed. Okay. So for each, so we construct a nominal group, and then we pick the individual from the nominal group, either randomly or according to one of those three criteria, and that's the comparison that we make, okay? And yes, so with respect to score, the highest scoring person is naturally the toughest baseline to beat, and the interacting groups don't quite beat it, okay? So let's try to understand a little more where this result is coming from. And the nice thing about doing experiments online is you have timestamps for everything, and so we can and we actually have the full every action that is taken. So we know not just what the solution is that was submitted, but all of the solutions that were attempted along the way, and in fact, even all of the partial solutions. So we can look in great detail at the trajectory that individuals take through solution space, or groups or individuals take to get to their final solution. So what we did is break down the total time into these four components. So the first one, T1, is from when the task begins to when the group or the individual first assigns all of the students to rooms. So that's what we call the first solution. And then there's some other period of time, T2, where they go from their first complete solution to their best solution, which is not necessarily the solution they submit. It's the best solution that they ever get. And they may or may not, well, they may not know that, right? But we will know that retrospectively, that this is the best solution that they will ever get. They then best solution to see if they can find a better one. And then they either will go back to their best solution, or they will sometimes go to a worse solution. And that will be where they stop. So that's what we call the final solution. But even then, having reached their final solution, they may continue to sit there and stare at it, or think about it, or debate each other about whether they should continue to try for a better solution. And finally, that process gets exhausted, and everybody agrees to submit. Okay, so those are the four time periods, and now we can look at the comparison across the same four categories for each of these time intervals. And so there's a lot in this figure. The top row is showing the raw data. So this is just how long they are spending in each of these states. And the bottom row is showing the same information, but in a standardized way. So we're showing it. Everything is now relative to the mean and normalized by standard deviations. Okay, and so that just has the effect of making differences more apparent, right? But it's the same data. So you can see that T1, which is sort of the setup time, T3, which is the fiddling with the solution time, and T4, which is the dithering before finally submitting your solution, all remain roughly independent of complexity, right? Uh, they're taking some amount of time, but it's not growing appreciably with the complexity of the task. T2 is very different, right? This is where you're really, in a sense, solving. This is the part of the solution that's actually really the solving part, and that is varying a lot with complexity. You can also see, going down to the bottom row, that that's sort of where all the action is happening in terms of positive group effects, or what we would call synergistic effects. That for the easiest task, there's basically no benefit to being in an interacting group, but by the time you go up to the most complex tasks, the gap there has increased considerably. And you can see that in panel D. You can see that they're all pretty close to each other for very low complexity, and that the gap has opened up by the time you get to high complexity. But the panel E just makes that difference more apparent. For the other time periods, T1, it turns out, somewhat surprisingly to me, that interacting groups are actually faster to get started. So there's a little bit of a synergistic benefit that, again, is unconditional on complexity. And then the last two time periods are where all the process losses happen. So groups, it turns out, spend more time fiddling with their best solution than individuals do, and they also spend more time talking about it before submitting it. So these probably don't seem that surprising to you. I'm sure you've been in groups that have done similar things. So individuals tend to be, better at recognizing when they've got their best solution, and they tend to be more decisive about submitting it once they have it. And again, those effects remain roughly constant over complexity levels. So we can sort of sum all of this up and say, what's the total benefit to being in an interacting group, which is just the time gain in T1 and T2 relative to nominal groups, and the total cost is the time lost relative to nominal groups in T3 and T4. And so that's the orange line and the blue line in the figure on the right there. And you can see that it crosses over nicely somewhere in the middle. And so we get this result that the synergy switches from negative to positive for moderate levels of complexity. Okay, what is happening here? Why are we not seeing, or in particular, why are we not seeing more of a benefit to interacting groups? If they're they're definitely more efficient when dealing with high complexity tasks, and maybe that's the thing that you really care about, right? In a real world setting, it's not clear what the right objective function should be if time is not a consideration, and small differences in performance and score is an important consideration. Then you might want to pick the solution where you get the absolute best score, no matter what the time what the time frame is. But in other situations, you may really care about efficiency, and so then you would go with interacting groups. Still, it's interesting to note that that they do not seem to outperform the best individuals, and so we tried to dig into that a little more. And surprisingly, I mean, there's not an obvious answer because groups compared to nominal groups, they generate more intermediate solutions, and they generate them faster, and they also explore more. So if you look at the solution radius, the difference between solutions, groups are picking are sampling more widely from the solution space. So all of those seem like good things. It seems like the ability to generate more solutions more quickly and over a wider range of the space should, in principle, lead to better performance. And so it's curious that it doesn't. One penalty associated with groups is that they are less likely than individuals to submit the best solution that they find. And we can correct for that. We can say, let's imagine, if we made some very simple modification to the interface and said, we're just going to save your best solution for you, then they would never forget. right? They could always just by default submit their best solution, even if they had wandered away from it. And if we imagine making that change to the interface, they would in fact get closer to the best individual. That's what panel D is. So panel D is where we now submit, we simulate a situation in which we have submitted everybody's best solution, even if it's not the one they submitted. And there the gap is getting pretty close. So even for most levels of complexity, it's indistinguishable, and for high and very high, it's getting close, but it's still not better. So this is a puzzle. We don't have a great answer for it. We can sort of wave our hands, but it's not clear to us, given that groups are doing all this very positive sounding stuff, why they're not outperforming the best individuals. So just quickly, what are we doing next? Jaren asked about group composition. We are looking at that. We can compare groups with other groups and look at how differences in average skill level or differences in diversity of skill level. So, what is the, having everybody at the same skill level versus different skill levels. We can look at differences in average social perceptiveness, and we can also look at diversity of cognitive style. So we can measure cognitive style in different ways, and we can ask, if you have different cognitive styles, does that improve or harm your group performance? And very quickly, the main result here is that if we just look at score, normalized score, then it turns out average skill and social perceptiveness are both positively associated with score, and significantly so. Skill diversity is surprisingly negatively associated with group performance, and cognitive style really has no effect, and nothing really has any effect for duration or efficiency. So that's if we just look at the a standard sort of regression modeling approach. If we ask, what factors or what features predict performance in an out of sample sense, then we see a somewhat different picture where the ranking of the coefficients is the same, but the skill parameter, actually the skill feature, is far and away the most predictive. So if you just have a model with a single feature in it, average skill level, you get an R squared out of sample of about 0.2. If you throw everything else into the model, it goes up to about 0.24. But most of the variance is being accounted for by skill. So social perceptiveness is there, but it's not really having a major effect. So that's future work. We can talk about it more in Q&A, but it's something that we're writing up right now. The other bigger project that relates to some of the questions at the very beginning is that we're well aware that this is just one type of task, and there are many types of tasks. And you could imagine that you'd get different results for different types of tasks. And so this, really, I think is the focus of Larsen's book. And again, surprisingly, this is not a question that has really occupied a whole lot of attention. There are certainly taxonomies that describe different types of tasks, but the exercise of systematically mapping out the space of task types and then sampling from that space, and then rerunning the same experiment over and over again to see how task type affects these kinds of results is not something that we're aware of has been done. And it's perhaps not surprising once you think about it, that it hasn't been done because it would require, a very different way of going about running experiments. And so we're in the process of putting together this, what we call high throughput lab experiments that allow us to run hundreds or maybe thousands of experiments like the one I just described. And, you can imagine that requires a lot of infrastructure and logistics to execute. So that's kind of the big picture. I hope that, in a couple of years from now, I can come back and tell you some answers. Great, thanks. You have some time for questions?
Yes, we've got lots of questions. Thank you so much. And so I'll let a handful of people unmute, but there was a question earlier that came back about thinking about incentive structures, if sort of the results would differ if you had sort of individual incentives or group level incentives or differential performance.
Potentially, yes. Yeah, I mean, I think, the answer to all of these questions is, yep, that could have an effect. We don't know. And really the only way to answer it, I think, is to do this kind of thing that we're describing at the end here of explicitly testing generalizability by looking at variations in all of these different parameters. Of course, that space quickly gets very, very large. I mean, just varying task type, we already have, I think, like a 38 dimensional space, which already requires some careful thinking about how to sample it in an efficient manner. If you then, throw in, every other parameter of the experiment, that the dimension blows up considerably. So we haven't thought about how to do that yet. We've been focusing on task type, but perhaps if we find very robust effects across very, very different types of tasks, then maybe it will seem less likely that some of these other parameters will have an effect, but not necessarily. And so I think that, certainly varying these group process factors, which I think is really what a lot of these questions come down to, would be interesting. And so if there are really, if there's like a top 10, list of group process factors that seem relevant, then that would be really helpful to hear about. Yeah.
I asked Patrick, do you want to ask your question, Patrick Park?
Thank you. This is really exciting results, and I really enjoyed it. Thank you for the presentation. My question is about learning rate. So maybe it takes time for group members to get to know one another's style, and for roles to kind of consolidate. So if you were to repeat these tasks, would the learning rate be different? Would it increase and even maybe potentially exceed the performance of the best individual in the nominal group?
It could. We did look at, so there is some potential for learning across, even within the scope of this experiment. So they're sort of together for some time between 30 minutes and an hour, and so you might think that by the time they get to the last task, they're on average doing better than in the first task. I don't think that we find that that there's not a sort of striking learning effect within the session, and I think also there's not a big learning effect between sessions, because we can compare individuals from phase 1 and phase 2, but none of that detracts from your question, because of course maybe we just didn't give them enough time, and of course in the real world teams can have a lot of time to learn how to work with each other, and so I think, another possible extension to this sort of framework is running experiments for longer periods of time, to test exactly this sort of thing. We've done that in another context. We've run a prisoner's dilemma experiment for a month, or at least we ran it for 20 consecutive weekdays over the span of a month. And we did, in fact, find some very striking over time changes. But just like everything, it's just more work, right? So, I think that would be a very interesting direction to go.
Thank you.
Monkson and John Maluser had similar questions. So Monkson, do you want to ask?
Yeah, I don't know if I missed it. I just try to ask the normalization of the performance by the group size. When you're comparing that, the group performance to the best individual performance, are you comparing it to, like, say, n best individuals separately, or you're comparing the best performance to the
So we sample without replacement 3 individuals from the same block, right? So if we're talking about the high block, we have teams that have high average skill and high average social perceptiveness. And so we then have a bunch of individuals in that same block who also have high average skill and high skill and high social perceptiveness. So we sample 3 of them without replacement, and then we pick the one that has from the first phase, either the highest score or highest average score, or fastest average solution time, or highest average efficiency, right? And then we compare to that person. So you're comparing to an individual, but you're taking the max over 3 individuals to make that comparison. Is that clear?
and you just think about it for a second.
So I mean, or you can take a random person, right? So that's like the equivalent of an average, right? So you either, are you looking at the average, and then you could if you wanted to, you could take the top 2, right, and compare it to those. But we're in some sense setting a bar higher by just taking the best person and saying that person. So if you from a managerial perspective, you might say, I'm going to give this job to the best person, right? I have 3 people to choose between. I'm going to give it to the best of them by whatever metric I care about, and I'm going to compare that to having them do it together, right?
Okay. So, but in terms of the efficiency or the duration, because they're kind of related calculation. So, if you spread a best performing individuals, I'm trying to say that like the best individual takes longer period of time, but if you take 3 person with less than 1/3 of the time to reach the same solution, like which one do you consider more efficient? I mean, does it make any sense?
If somebody got almost the same score and they did it much faster, they would be more efficient. Yes.
Right, but if the
compare efficiency to that person. So typically the best performing person is not the fastest. They could be, I mean, in theory they could be, in which case they would also be the most efficient, right? So the best, fastest, and most efficient could all be the same person, right? In any group of 3, but typically that's not the case, right? So depending on what your metric is, you'll prefer a different member of the nominal group. So we're always, in some sense, giving the nominal group the best chance it can get to outperform the interacting group, which is why they're hard to outperform.
Thank you.
Yeah. Mark, do you want to ask?
So do you have any way of telling what kind of collaborative techniques the groups are using to improve their performance? Like, do they divide up the task in some way? Do they appoint a leader? Do they delegate tasks? Do they communicate in particular ways? How are they achieving these higher performances?
Short answer is no, we haven't done that. But I think one could do that with the data that we have. You could try to do some sort of partitioning of to look to see if they've in effect chosen different groups, subgroups to work on. So one way you could imagine people do this is they say, okay, I'm going to take students 1 through 4, and you take students 5 through 8, and you take students 9 through 12, and then we'll once we've allocated our students, we'll like get together and resolve conflicts, right? So one way to try to detect that might be to look in the chat and see if they've actually used certain keywords. Another way might be to look at the data itself and see if in effect we can find that we can identify that different workers are focusing on different students, but we haven't done that. So it's a good idea. Now what we have thought about is actually baking that into the design, right? You could easily modify this experiment so that people had either distributed information or distributed control, or both, right? So you could say, everybody gets to see all of the students, but you only get to move 1/3 of them, right? Or you could make it such that you only get to move and you only get to see the score, the payoff scores for those students. So you could have distributed control or distributed control and information, and that would also probably change the results. But yes, it would be nice if we could detect some kind of division of labor, because that's where you would expect to see big performance gains. And going back to Patrick's question, you might not see it in the time scale that we have, right? So we know, we probably know in the real world that division of labor is like maybe the single biggest positive effect in terms for groups, right? Going back to sort of Adam Smith and the pin factory, you see returns to specialization that can be enormous, and you get that from division of labor. So it would be great to see if we could generate that in a lab setting. It's just tricky to do with undifferentiated workers who are learning the task. But big picture, I would love to do that. Thanks.
I'm keeping an eye on the time, but Jaron, do you want to?
Sure. Yeah. Great as always. Duncan. So I especially loved the slide about the milestones, and I was thinking the fact that the teams are spending so much time at the final stage, maybe is sort of making a case for having more incremental systems for teams. So like the example I'm thinking about is Wikipedia. If people had to agree on the final article, nothing would go out.
Mm-hmm.
And so I was thinking, what do you think about if you allowed teams to submit submissions with an option to submit more later on? What would you observe?
Yeah, you could. I think that what it suggests is certain kinds of nudges or interventions that might help teams do better, right? So, appointing a leader might help, right? You just put someone in charge, and then they could submit the solution. Then you kind of get the benefit of, the team, and also get the decisiveness of an individual, right? You could, remind them. You could give them a message and say, "Looks like you've got the best solution you're going to get. Why don't you submit?" And that might sort of speed things up. So I think, again, we didn't try any of these things, but I think that this style of analysis does provoke these sorts of questions about how you might, once you can sort of pin down where the process losses are happening, you can, just like saying, "Oh, we've saved your best solution here just in case you need it," right? sort of simple interventions like that might help groups do better. And whether they work in the real world is another question, but I think that's, absolutely the kind of direction that we're hoping this will go in.
All right, it's about 12:45. I just want to thank you again for joining us. We often either turn on our cameras or clap in some mode, but thank you so much for coming and sharing with us. Great to
Thank
hear.
you all. Nice to see you.
Thanks.
Hope to see you all in person one day.